Okay, so very happy to be here. Have an opportunity to share with you or more report to you a study we did of equivalence principle test experiment on International Space Station. And as some of you know that the JPL in collaborating, working with NASA is actually building a cold atom laboratory, BEC, a facility going to be launched to International Space Station next year. And this is a sort of a possible follow-up of experiment that can be done in the fundamental physics program. We had a fairly big team of study in this concept, and we have scientists at the JPL and also working with Holger Muir's group at the University of California, Berkeley, and we have a whole bunch of engineers participating in the study, both for the science feasibility study and the engineering feasibility study. And so the science feasibility study part mostly described in detail in this New Journal of Physics article late last year, and so this is what mostly I'm going to talk about today, and there are a whole set of engineering studies that I'm not going to talk about, so if you have any questions, I'm happy to talk about afterwards. So in a nutshell, what we're trying to do is basically measure the gravitational acceleration difference between two atomic species, in this case rubidium 85 and 87. So according to Einstein's equivalence principle, everything should fall exactly the same rate regardless of the size and shape and the composition. And the motivation of testing the Einstein's equivalence principle are manifold, and it is really a foundation of general relativity described in the gravity, and so you always want to test as precise as you like to, but that sounds like a little bit more self-serving. But as some of the talks in the plenary session and also in Mike's talk, that there are a lot of physics that we don't understand. And for one thing, gravity cannot be quantized. And so this, in the attempt of unifying all the known forces of nature in the grand unification theory, there are models that can predict or lead to the violation of equivalence principle. And in addition, that we know we know pretty sure there are existence of dark energy and dark matter, and if dark energy is actually scalar, light scalar field, then there could be interaction with normal matter that leads to the violation of equivalence principle as well. And so for all those tests, you can actually parameterize the sort of test in sort of a standard model extension, and basically just saying that the gravitational acceleration, there's an additional term, beta here, and which is can result from a number of different type of interactions that, of course, these interactions are new physics are unknown. And so the objective is then to look at the search for the beta or put limits on these values. So the way we do it is so-called using a cold atom as a test mass, and use atom interferometer as an accelerometer for the measurement. So I'm not going to actually talk too much about atom interferometer, but for those who are not familiar with it, atomic particles, of course, also behave like a wave particle, wave, and so you can actually use laser pulses to split and redirect and recombine atom waves and form a sort of Mach-Zehnder interferometer. And in the end of the day, after you complete the interferometry measurement, and you come up with a phase shift of this matter wave interferometer, which is proportionate to the acceleration that's experienced by the atom. And for those who don't care really get into the atomophometry, a simple picture of it is that the atoms have internal oscillation as a clock, and these clocks are falling in the gravity, and your light pulse sets sort of a ruler in the space, and so register, you can think about either phase or frequency of the falling clocks, and therefore you can actually measure the minute changes as a result of forces acting upon atoms. So the objective, the science objective of this experiment is really to achieve 1 part 10 to the 15th of a differential acceleration measurement between rubidium 85 and 87, and this, of course, as you most of you know, that the best equivalence principle test today are the pendulum experiment Edwards that at 1 part 10 to the 13th, and this is also at the same precision of a neural ranging equivalence principle test, and so this will put sort of 100 times better than what has been done on the ground. And I should point out at this point, actually, there's another classical equivalence principle test mission called a microscope from Kinect and ESA just launched last month that have classical test mass of orbiting Earth for testing of equivalence principle, and the expected precision is also at 1 part 10 to the 15th. And so the difference here is we're using free fall atomic particles or wave functions, so they are connections of gravity with quantum mechanics, and also there are some specific in a new physics model that some of the violations may not be seen in the dense, high density matter, but could be seen in low density atomic test masses. And there are secondary objective of looking at the photon recoils, and I'm not going to look into details, but they have to do with actually relates to mass standard to frequencies, and also high precision measurement of fine structure constant alpha that relate to quantum electrodynamics. So obviously this is a space experiment, so you have to first justify why you want to do it in space, and it's fairly clear and long recognized that if you have free fall test mass, and so in a free space in a weightless or microgravity environment, you have very long interaction time with the atoms, so you achieve a higher precision. But less appreciated is actually the fact that the satellite orbiting around the Earth, the gravity direction actually modulates as the Earth rotates, and the rotation or modulation of the gravity field give you a powerful tool to mitigate some of the systematics, which is very hard to overcome. And so our strategy of this experiment is really based on the beating down the systematics in sort of most symmetrical measurement way as possible, and modulating to beat down the systematics rather than try to understand what the systematics is. And so this allows us to achieve what we think that we achieve 1 part 15th, even on the International Space Station, which is not quite the quietest platform that in space. And so the way we do it is, of course, we want the highest flux atoms possible to boost the signal noise. And we do the gravity modulation, which turns out to be a critical component of the measurement scheme. And we do the Bragg diffraction, which totally get rid of sensitivity to vibration. And I'll talk more in detail in the following slides. And imaging detections to recover some of the contrast loss due to various inhomogeneous effects. And looking for ways to do the gravity fringe compensation, which has been a big problem for people who are working in this field. And so this is sort of a kind of cartoonish schematic of what the payload instrument is going to look like. So we have a science chamber where the actual measurement is going to be performed. And we have two sources. So basically, we actually have two sets of dual species interferometers that are propagated in the opposite direction. And that gives us actually k-vector reversal for taking out of those systematics, which has dependence on the direction of laser. And so you start with a 2D magneto-optic trap, the source to load into the 3D mark, and then you transfer to a magnetic trap, and over there you do the evaporative cooling, sympathetic cooling, to get atom to very cold temperature. It turns out in space you can get it much colder. And you do a delta kick cooling to get nano Kelvin. Then you do atom transport to transport the atoms into the science chamber. And then you push the two atoms in opposite direction. So this could give you a sort of opposite direction of K reversal, because the laser direction is only one in direction. And now you start your so-called atom informator process, and so you will fire one and split the atoms, and then you redirect them and recombine. So that's standard pi over 2 process to complete the atom informator. And at the end, you do imaging detection, and of course, this just shows one set of interferometer that's a simultaneous measurement on the other direction. Now, after you've done a few such measurement, detection, after you've done such a measurement, then you can rotate, you put this whole apparatus on a rotating platform, and then you can rotate the whole thing relative to Earth. And the reason you do that is because it turns out the International Space Station always pointing down in the same direction, so it doesn't give you the automatic gravity modulation. So we put it on a turntable so we can reverse the direction of gravity. Anyway, and so the reversal or modulation of gravity, you can think of most of us using, at one time or another in the experiment, using a lock-in amplifier. And the simple way of looking at the lock-in amplifier, that if you modulate your signal at a certain frequency, and you can average over a period of time, basically shift your signal to a different frequency band, and you can do the detection. So over 3 months of measurement period, you can actually suppress such a NA of systematics by a factor of 10,000. And this is sufficient for some of most dominating effects that to be suppressed down below 1 part 10 to 15. And this is the only actually engineering model I'm going to show. This is sort of the instrument that looks like on a turntable, and the whole thing is actually fairly large. About would be about the turntable itself, just shy of 1 meter in size. And this is a science chamber where the measurement occurs, and these are the two sources and the magnetic trap for evaporative cooling and the transport. And there's a ritual reflecting mirror, which has a set of gyros on it, and I will talk more why we need that for correcting the Earth's rotation. So one of the first questions that we'll ask that when actually we come up with this modulation scheme is that you have all the optical fibers connected to the turntable, and what would be the effect of when you rotate the table. So one of the things that we actually try to did a measurement is how light can change as it rotates on a turntable. It turns out that the intensity change of light through a very well-aligned polarization maintaining fiber will be less than 1.1%. So I think at this point we are pretty confident that this will not have significant effect. But whether this is indeed will cause any correlated effect as we rotate the platform still need to be have some more detailed simulation. But so in terms of source, and so we actually adapt to use so the so-called, well, not exactly sort of free space, but sort of not chip-based, mainly because we like have a more symmetric, high flux source. And so the estimate shows that we can get 1 nanokelvin temperature with millimeter atoms, so get sharp noise, limited signal noise of 1,000. And see, I actually run out of time very quickly. So I'm going to run through these things quickly, and this is one way to do the transport is use the block oscillation, basically moving the two species in optical lattice, and because the two species actually have slightly different mass, so you have to transport them in a way that the total displacement, the overlapping two species is going to transport to the sine chamber and still maintain overlapped. Now, one of the things I really should point out is that we chose to use Bragg atom interferometer rather than Raman-based atom interferometer, and the Bragg atom interferometer really not rely on internal state of the atoms, but just the same state, just different momentum state of the atom. In doing so, one of the biggest advantages is that we actually can find a magic wavelength of Bragg laser beam. So the two species of rubidium atoms with different transition frequency would have exactly the same Rabi frequency in terms of Bragg oscillation. And so now you have two species actually run on exactly same laser system or laser frequency. And so everything, the laser frequency and the acceleration it's all common to both species. So you have a high suppression of vibration, which is very important on the International Space Station because the vibration environment is not all that great. Just briefly mentioned, so there's some residual second-order Zeeman shift of different species have a different shift, and so what we plan to do is take advantage of the fact that the upper state, the F1 and F2, actually have different signs of shift. So if you alternate the measure up and low state, you can cancel out just like you do in most of the optical clock nowadays. And the other thing that important or big challenging in actually measuring using atom interferometer in an environment where you have a gravity gradient is that because your precision is so high, the phase shift, just because of the initial location and the velocity of atoms, will result in a large phase shift that completely wash out your fringes. And so one way to do that, as shown by this paper, is actually add a somewhat open atom interferometer to compensate the velocity. And this is some didn't seem to show. Anyway, there's a picture missing here, so you can actually recover the fringe very, very nicely. And so with this fringe recovery and with the gravity gradient rotation, you can totally suppress the gravity gradient effect. And there's some, the effect of gravitation gradient suppression is not all that obvious, so I like to just say very briefly, so in terms of how one can suppress the gravity gradient effect. So if you have gravity in this direction, so you can think of Earth on this side, and you can sort of plot your gravity vectors like this. So the vectors going down. Now, if you actually turn your Earth to the other direction, and what the vector field looks like is completely going down like this. But as far as the gravity gradient goes, this is the derivative or slope of this, so they are exactly the same. So as you rotate the g vector, the gravity gradient actually doesn't change, and so your equivalence principle signal alternate, but your systematic still to the gravity gradient is not changing. Therefore, you can suppress that. So I'm going to sort of stop that, this is just a mathematical rendition of why, because second order derivative, you actually it's invariant on the rotation. So I'm going to skip all these things here and just say that all the systematics, if not for the statistical values, we can actually suppress all this to 10 to the minus 18th level. And so it's a matter of really how long you want to be able to average down to your systematic. So for a 1 year, 3 months to 1 year period of time, we can get 1 part of 10 to the 15. So this is really just limited by the averaging time we can have. And so I'll leave this as concluding slides. So basically, we can get into the 15 things in 3 months of averaging time, and these are some payload information. Not exactly small, so pretty rack-sized instrument payload. Thank you.